Hello and welcome to the 10th webinar in 12D's training webinar series. My name is Lisa Stewart and I'm the Marketing and Communications Coordinator at 12D Solutions. While we wait for everyone to finish joining and get comfortable, I'll launch a polling question. You'll have about 30 seconds to answer about what you use for your current culvert design, and then I'll show the results. Okay, it looks like most people are using rational method, but we do have a few people who understand that it's a dangerous business, so I'm glad. Welcome everyone. Our 12D training webinars showcase common industry challenges, taking a close look at industry best practices and how these can be implemented using 12D model software. The aim of these webinars is to upskill 12D model users and broaden their understanding of the capabilities of 12D model. We'll keep running these webinars regularly and recording them for posting through our website and on YouTube. The first 9 webinars from this training series, as well as the first 14 webinars from our Industry Solutions series, are available online if you missed those. During this live presentation, you'll be able to type your questions along the way, as shown on the screen, and we'll answer as many as possible throughout the webinar. At the end, I'll also read out some of your questions to the presenter for his insights if there's time. Today's webinar, Culvert Design with Upstream Storage, will be presented by Rob Graham, our resident water resources engineer. Rob has almost 20 years of experience here at 12D and over 30 years of experience in the industry. This webinar from the training series will explore the way in which many culverts are sized on the basis of the peak flow rate from a hydrological analysis. However, with the storage volume at the upstream side of most culverts, the peak flow rate through the culvert is often less than the hydrology method indicates. The dynamic drainage module will automatically account for the storage volume and allow for a more refined culvert design. Over to you, Rob.
Great. Thank you very much, Lisa. Today we're going to be investigating various methods for modeling culverts with upstream storage. We'll begin by taking a look at the rational method that many of you indicated that you are currently using. And of course the rational method has no capability for looking at upstream storage. And also your hydraulics is done via hydraulic grade line check. After a quick review from that, we're going to move on to the main topic for today, which is how we incorporate upstream storage into the culvert design. So this will involve using hydrographs, first of all with 1D modeling, and upstream of the culvert we'll either have channels or we'll have flat water basin storage. In order to calculate the flows through the culverts, in these cases we're going to use unsteady flow hydraulics, which is solving the St. Venant flow equations. After we've done a quick look at, actually a fairly good look at the 1D modeling, we'll move on and take a look at 2D modeling using the TUFLOW engine. In this case, we'll use the same hydraulics to calculate the flow through the culverts, but we'll use a 2D engine to calculate the water levels upstream and hence the storage upstream of the culvert. So let's jump into 12D and start taking a look at a project. First of all, what we're looking at here are 3 screens. On the left-hand side, we've got a bit of survey information. In the center of the screen, we've got a section view through that survey information. And on the right-hand screen, we sort of have the end-of-the-day pictures where we're looking at some upstream storage going through the culvert underneath the highway and exiting through the tailwater channel down below. So let's just take a quick look at how culverts are created inside 12D. This isn't going to be the focus, but we might as well just take a quick look at that. So generally, in this example anyway, we're going to look at a surveyed culvert where the surveyor has gone and picked up the invert levels of the culvert. So I'm going to toggle off my raster for a moment so I can get a closer look at the surveyed line you see across the road. And then I'm going to come back and toggle on my Z values. And if I zoom down a little bit closer to the head wall and where the pipe is, you can see the level has been picked up by the surveyor, both the upstream invert and the downstream invert at the other end. So when it comes time to create a new drainage string, I'm going to use the menu system for the time being, but of course you're more than welcome to use our toolbars down here for drainage. So the first thing we should do is just take a quick review of our defaults. The survey tin is what we use to measure the cover above our culvert to the surface to make sure that's adequate. And so we'll make sure we've got that set to our current survey tin. The manholes or the structures, we want to set that to the head wall inlet auto. And this is very critical that we do this. Not so much at this moment, but later we want to ensure that our head walls are set to be using the inlet control nomographs developed by the United States Department of Highways in their culvert studies. So that's a pretty important one that we make sure that one gets set. Often I just use a 0 diameter for the upstream end. That's optional. So we'll go and hit set that. The next default we take a look at is our pipes. Now I'm going to drop down here and take a look at this one. The choices we have down here, we're going to use an RCP for this one, up here at the top. And let's start out with a 525 pipe. That probably will get resized. And we'll hit the set button on that. So those are the defaults you'd like to set before you go to the trouble of creating a new culvert. Now because the surveyor has been kind enough to pick this up for us, we're going to use the create from string option. And then we'll go pick that string that the surveyor would have picked up. And our job is to once again mention the tin that's going to be used for the tops of the covers, and then to put it into a model. I'm just going to create a model called Stormwater New, and we'll hit the create button, the process. Now in this case I'm only doing one string. We could have easily done a whole model of strings. So now I want to take and add this onto my section view. So if I come across here and add on this model called Stormwater New, there would be my culvert coming across the roadway. And if I use my profile button to come select that culvert, that is my original survey string. That's the culvert itself. We would be back in the same situation, except this time I specified a smaller pipe. So you can see there's not much involved. It's not very difficult at all to create a culvert inside 12D. Now let's move on and start taking a look at some of the design of the culverts. So I'm going to move across to a new view over here. I'm going to head to a design view, and I'm going to look at a culvert that I have already created, and it's in my model here called Stormwater Design Rational. And then I'm going to use our network editor. Now our network editor is the heart of 12D's hydraulics and hydrology. So I'll select that network editor, and I'm going to come across here. I'm going to pick the upstream end. Now I mentioned earlier how important it was that we select a head wall culvert when we selected our pit types. And there it is at this end. Now the important part of this is down below, it changes our KU method. Now the KU method is generally attributed to losses at the entrance to the pipe. And of course, when it comes to a culvert, what we're looking at is inlet control. Because our concern for culvert hydraulics is to know whether we're running under outlet control or inlet control, and making sure we select the result that gives us the highest water level, or if we're doing dynamic, that gives us the lowest discharge. So we have that done. That's very important. If we were to come back and say that we wanted a different type of head wall, we'd remove that auto setting and come down to just plain in setting, and that would release our locks on the types. And you can see that inside 12D we've got a wide variety of head wall types. Each one of these head wall types would have a different inlet nomograph and would have a different entrance loss coefficient when it was operating under backwater controls. So having taken a look at the hydraulics, that's the big step that we need to make sure that we're going to be calculating this using the inlet nomographs. Let's now just switch over to a quick look at the hydrology. I'm going to head to my catchment tab over here into set number 3, and I've put in here 28 hectares of catchment area upstream. So if we were to zoom up here, what we're looking at is the catchment area up above here. Now typically users would draw a polygon and we'd measure that area for them, but I'm putting in nice even numbers today so that we can round them off and change them in the future. So we haven't used the polygon today. Now, times of concentration and the C values. If you're used to the rational method, you're well and truly comfortable with those. And what we'll do now is switch over to our global tab. And of course the next part is to make sure that we use the IFD information, the rainfall information, from your local area. Today we're using some rainfall data from Perth, and with that, let's go and run a storm analysis. When we run our storm analysis, we're going to run a major storm here, a 50-year return period, and when we do this, we're also going to ask for some flood extents to be calculated in the upstream area. So let's go give that a run. If I take you back to the main tab, one of the unique features, or really nice features, of our rational method is that it will size the culverts if need be. And what we'll do is we'll check the hydraulic grade line against the grade level and make sure that's high enough. So let's come back and see what we have. And we've got some drainage labels here. We're coming out on our drainage labels. What this will tell us is how much water is flowing through our pipe and how much the catchment flow was upstream. You'll notice the same numbers. We have no storage in the upstream reaches, so whatever the peak catchment flow is from the rational method, that's the flow that we're going to be putting through the pipe, assuming we don't have any bypass. Now, in our training webinar today, we're not going to have time to take a look at the bypass. And of course, bypass from culverts is definitely important, and it will be the topic of a future training webinar. So let's go back to the editor there. There's one very important level inside 12D hydraulics. And just take a moment while I go profile this culvert that we just solved. And at my labels, that's the one I'm looking for. It's the grate level. If I go back to my pit tab and go take a look at the grate level, you'll notice it's been set manually. Now, most of you would be aware that there's rarely a grate on a head wall for a culvert. What the grate level represents for us is the level at which water will bypass from the head wall and go some other route over land. And typically what we would do if I was looking to discover this level, I would go and add on my tin survey, and I would come back and I'd put on my tins inquire height, inquire height, and I would go check a look at my contours upstream. And I would see that this is going up in this direction. If I was having trouble with that, I'd probably come and hit my F11 key, ask for some flow arrows, maybe about 2 meters long rather than 10. Set that. And now I can see the downhill direction. So I'm pretty confident that roughly at elevation 32, that's when I get the overflow. And it's not going to go over top of the road. It's going to head down the side of the road. So that's how I would set my bypass level for the culverts. Now, when we ran the design, just a moment while I turn off that tin, just to keep the view a little bit clearer, you might have noticed that we're getting roughly 2.3 cumex through the culvert here. And also, in order for that to work, we changed this over to 2 culverts, 2 600s. When we did the design in here, we asked that the maximum pipe size was 600, and that's why it selected 2 of them. So what I hope to do there was just a little bit of background into the rational method side of hydrology. And now I want to step forward into the main topic of today, which is the dynamic with the upstream storage. So on my design view here, I'm going to just turn off those labels and that stormwater design rational. And I'm going to bring the same culvert back up in another model, but set up to do the dynamic analysis. So stormwater design dynamic. Of course, when we're looking at the culvert here, it looks exactly the same. But when we go select it with the Drainage Network Editor, we're going to take a look at the different properties. First, we'll review back to the most important ones. We'll go back to the pit tab. Of course, that grade level is exactly the way we left it. And we are looking at the same culvert standard 45-degree head walls. So that part stays exactly the same. When we move across to do our dynamic, we're going to switch from the rational method over, and to this case, we're going to use the Ilsak's method. So if I went over to the Global tab, you'll see that we've selected the Ilsak's 2 method here. We're still going to use the Perth rainfall. When you use the Ilsak's method, we have to start taking a look at the infiltration. So rather than the C values for losses, we're going to look at 2 other forms of losses. So the first one, we are using the Horton method. And when we're using the Horton method, we are going to need to know the soil type and how wet the soil was prior to the start of our design storm. This is referred to our antecedent moisture conditions. In the Ilsak's method, a value is assigned between 1 for dry and 4 for completely saturated. So we're going to run almost completely saturated in this case, and we'll find that the discharge, especially on large basins, is fairly sensitive to that antecedent moisture condition. I'm going to change that to 3.4 before I do this run, and you'll probably see why in just a moment. Now the other parameters I mentioned, if I go back to my defaults and look for my set number 3 here, actually let me go to my catchments for this one, set number 3. You'll see that we've got the same 28 hectares, we've got the same time of concentration. The C values are not being used. Once again, we're going to have new parameters. The parameters that we need for the Horton are going to be the soil types, and those soil types will determine the infiltration rates. So I'm going for type B soil here. Any water that does not infiltrate on the ground will pond up on the surface before it starts flowing off. And that's what this storage is. What this is indicating here is that there'll be 5 millimeters of storage on the ground surface before we start to get the runoff. Now to keep this as a nice simple example, we've gone with the percent impervious of being 0, and that's being set on my defaults, and so we're using only the pervious component. We could just as well use both, but I think that'll keep it a lot simpler for this example. So quick review there. We're using the same time of concentration parameters of the rational method, and that controls the triangular unit hydrographs. But instead of C values, we're going to be using the storage on the surface, the soil types, and the antecedent moisture conditions. The next thing we need to do is we're going to have a variable temporal pattern. The rational method used a constant rainfall over the time period chosen, time of concentration in most cases, and in this case, we're going to have a varying temporal pattern. So what I'm going to do is I'm going to open up this Perth rainfall file just so that you can see what's involved. Oh, that across. Managing my real estate here. There we go. So inside, of course, we have exactly the same IFD information, and we were running that 50-minute storm a while ago. But now when we start looking at the dynamic, we need to start looking at temporal patterns, so how the rainfall changes over time. Let's take a moment just to look at that 25-minute storm. If this was a constant rainfall over 25 minutes, those 5-minute intervals would be 20% each, all adding up to 100. And you notice that's not the case here. As a matter of fact, by the time we hit this third period, it's almost double. So this 25-minute storm is going to have very high rainfall intensities, and that will affect small catchments. Larger catchments, or areas with storage, it may become more dependent on longer storms. So when we go to size our culverts and to check the maximum upstream water levels, we're going to want to run several storms, which is what we've done in this case. Now just a brief look back where we're at the Horton losses. Those are those soil types that we described. That's the initial loss in the soil if it was completely dry. That's that antecedent moisture condition 1. The final losses are when the soil is completely saturated, and that's very close to antecedent moisture condition 4. And this 2 describes the decay rate. So we're going to use this type B. So the initial losses are going to be about 200, getting down to about 13. And we're going to be starting very close to the 13 at the end. So that's just a little bit of a background into the hydrology that we're going to be using. Now I want to start getting back to the main focus, which is the upstream storage. So let's zoom out here just a little bit. Let's add that tin back on. And as we looked before about this elevation 32, there's going to be a whole area inside here that's going to fill up with water before the water can start flowing through the culvert. Essentially, it will be acting as a stormwater detention basin. So what's involved inside 12D for this is we'll go to the Pit tab, head across to the Basin tab, and what we need to do is we need to pick a polygon which we feel is the extent of the ponding on the upstream side. Now there's several ways that we could pick this polygon, create the polygon. I find the easiest way for me to do it is to take a look at the contours, figure out what I feel the maximum is, and then ask for the contour to be created. Now 12D is very quick at creating contours from tins, and generally we would come down and we go to the tins, contour, smooth and label, and this comes out with some preset defaults for it, but essentially what I would do is I'd put in a minimum and a maximum value being the same, and that being the contour that I'm interested in. When I process that, if I was to come add on that culvert, which is my stormwater contours, essentially what I've asked for is all the 32s, and this is the 32 contour that I'm interested in. Now the beauty of this is that if I want to get the area storage curve for that, all I need to do is go hit the pick button, come over here and pick that string, and 12D very quickly goes and measures the areas at a 0.1 meter interval, and will plot that up for me. Now this is a bit small to see, so I'm going to do a right mouse click on here and maximize this. And the first thing it did was create the elevation versus area curve that you see here. Now once it had the area curve, the next step that we do is we take that and we calculate the volume. And then here in the red you'll see that's the volume curve that we have for this basin. And it goes up to our 32. We just passed it. One of the questions we sometimes are asked is what happens if we went up at a finer interval because of the shape of a basin when you're using the average area method. It's theoretically possible that if you go up in smaller increments that you can get slightly different volume calcs. So what happens is we do an interpolation. Of course, the first time we did this, we did the results. Let me go back here, mark the data points. We calculated the areas every 0.1 of a meter. So what we do then is we repeat the calcs and we interpolate the areas every 1/10 of that and recalculate the volumes. So essentially in this case, hopefully you feel somewhat more comfortable that that approximation is valid and that you can't even see the difference between the blue and the red. They're right on top of each other. A settle point in our volume curves. So once we have this volume upstream, the storage volume, we're ready to go and run our analysis. So we'll head across to our storm analysis. And once again, we're going to run the same 50-year rainfall intensities. We do use a separate plot parameter file for getting our results, and I'm putting the values into a different model so that we can look at them. So they'll be called drainage labels ILSACs. Let's go and run our dynamic engine. When we opened up that rainfall file, there was 5 storms that were selected. And it's currently running all 5 of those storms. And then we're going to find out what the maximum results are for all of those storms. And that's what we're going to plot in our long section views. So I'm going to turn off the tin once again just to clear up the view a little bit. And I'm going to add on this model called Drainage Labels ILSACs. So if we take a look here, we've got an approach flow that's approximately the same as last time. They're not exactly the same. But if you take a look at the flow through the culvert is approximately 300 liters per second less than the approach flow. So what's happened here is in the upstream area, it's gone and ponded, acted like a detention basin, and slowed the output. Let's go take a look at this from the perspective of some graphs. With the dynamic, because everything changes with time, it's pretty important for us to see our results in graphical form. We went and did some major storms, so I'm going to select my major storms, and I'm going to ask for all my design storms. And I'm interested in the maximum water level, so I'm going to ask for my elevation graphs. And I'm going to do a right mouse click and maximize this so we can take a good look. And you can see we've run the different storms. There's the 4 of them, pardon me. And you can see here that the one in bold, the 25-minute storm, is the one that's given us the maximum. So I'm actually going to focus on that 25-minute storm just for a bit. If I wanted to see the flows that were going through the culvert as a result of that, I can come down and ask for my flows. And I maximize that. And as I'm not surprised that with the maximum headwater, and that's not always true, but usually the maximum upstream water level will give you the maximum discharge. Of course, that would depend on the tailwater conditions. And you can see that that's given us the maximum flow. You might also notice that they're fairly rounded. What's rounding our hydrographs is the fact that we've got that storage upstream. If I was to come back instead and ask to see my runoff from my set number 3, those are not going to be as smooth. That's the actual hydrograph that's flowing into the basin. And so what happens as it gets routed through, it sort of takes off a bit of the edge. And of course, N reduces the flow. So what we've just seen through this quick example is how the flow is attenuated by going through that stormwater basin. If we come back and take a look at one other graph, if we come back and look at just our 25-minute storm, one of the things we can ask for is our total inflows and outflows. Now I go maximize this. With the total inflows and outflows, what you get to see is first of all, you can see the elevation. Okay, we've seen that before, it go up and down. That's the maximum that we've observed. But the other thing you get to see is the maximum inflow in your basin and the maximum outflow from your basin. And that difference there is the attenuation, and that attenuation in flow is what allows us to have smaller culverts to carry the flow. So that was the first point that I wanted to talk about. If we flip just back to our slide for a second, we want to take a look at the hydrographs and take a look at them with flat water storage upstream. And for that whole solution there, we're using the St. Venant equations in order to calculate the flow. If you're unfamiliar with the St. Venant flow equations, probably the most important feature to recognize from them is that the flow through the culvert is dependent upon the hydraulic grade lines. So the pressure upstream and the pressure downstream determines the flow through the culvert. It's not done the same way as a hydraulic grade line check where you're given the discharge and you calculate the water levels. So it works in the opposite direction, and that way we're able to model the physical processes. What determines how high the water gets on the upstream is continuity. If more water approaches the pit, then approaches the head wall, then can flow through the pipe, it'll fill up. And that's what happens at the beginning. As soon as the flow starts to decrease coming in here and it gets below the outflow, the water starts to drop down and it drains out. We can see that happen in one of our graphs. One of the favorite graphs for people to take a look at is our dynamic link results. Oops, not our all link results. That one might be my favorite. But let's go back to the dynamic section. That's what we're looking for. And if I hit the play button on that, what it'll do is it'll show us how the water level goes up during the storm, and then if we keep playing that, eventually drops down. At the end of the storm, it comes back down. So that gives you a quick look at what would happen if we took a look at that as time changed. All right. The next step that I wanted to take a look at was, what if we were going to model this upstream storage not with 1D modeling, not with a flat water detention basin, but rather with 2D modeling. So what I'm going to do is we'll just go and close this drainage network editor for a moment. I'm once again going to switch culverts on you. We'll take these ones off. And I'm going to add another one on. That's my stormwater design 2D. So what's going to be different when you do 2D analysis is the upstream catchment area is going to be divided into a grid. And that grid is going to create the storage for us. If you thought of it as a very large ice cube tray, it's probably the best way to think of it, with each one of those places where your ice cubes are made is a little storage cell. And each storage cell would hold a little bit of water until it reached the edge when it would flow over it. So we'll take a closer look at that when we go on, but that's the idea, is the storage is going to be on the upstream end. So let's grab our drainage network editor again just for a moment. Take a look at that upstream end of the culvert. And one of the first things we'd want to ensure, of course, back to making sure we're using that head wall auto, but also we would not want to have the basin on here. If we kept that basin data, we'd be double counting the storage. So let's go clear that out. We'll even get rid of that string as well, so it doesn't get remeasured. So now we know they're not doubling that up at the end. So we'll do apply and we'll do a finish on that. All right. So now we're going to take a moment and we're going to look at TUFLOW. The basic inputs for our TUFLOW model, if I bring up TUFLOW, once again, I've saved the input values for these panels so I don't have to spend too much time typing them in. And the very first thing we need to take a look at is what we call the TUFLOW grid extents. So let me take a look. I've got another view here just for my TUFLOW inputs. So what we're required to do is to draw a rectangle around the extent of our project. So when I did this, I made sure that I was able to get enough downstream so that I could see what's happening to my tailwater, and that I'd have enough upstream so that I would be able to see the storage at the upstream side. I've gone with a very large cell size for this. I've gone with 5 meter cells, only because I want it to run very quickly so that I can do the runs live during this presentation. It would be better to, in this case, to use smaller sizes, but it would take us a little bit more time than I think we want to spend during this presentation. So the other important value is the default end value for the roughness upstream. We're going to use our original tin, that's our survey tin, and we're going to create a new grid that is going to be sent to TUFLOW to do the analysis. On the optional data side, the most important one I want to talk about here is our stormwater culvert. That is going to be linked up to the, you think of it draining one ice cube tray cell and filling up another cell on the other end. This culvert's going to take that water from that one cell to the other. Another important feature when you're doing your TUFLOW modeling, or two-dimensional modeling, is to make sure you model your ridges and your gullies accurately. We're not here to talk too much about 2D modeling, so leave them aside for now, but just know that the ridges and gullies are an important part of the process. So let's go hit the run button on this one. Road flow erases all of the current runs before it starts, and we're going to run 5 different TUFLOW jobs. TUFLOW refers to them as events, so 5 different rainfall events, and each one of those is going to be a different storm. So we'll be running the 25-minute storm, the 30-minute storm, the 45-minute storm, the same ones that we did for the dynamic 1D. Now they didn't take too long. Now you can see why I wanted to keep it fairly small. And we're ready to read those results back in. When I go to read the results, I do have to select which storm I want to take a look at. When we did the dynamic 1D, it was the 25-minute storm that was critical, so I'm going to select that one for our viewing. And I'm going to go read those results in. Now once the results have been read in, well, first I want to take a look at these in a 3D view. Now let me turn off this model. This is the one that we're going to take a look at later. And I want to take a look at the one that we've just selected down here. Our culvert stormwater design 25. And that's the maximum from it. So now what you can see is, just like we did with the 1D modeling, but without quite as good annotations, we're able to see that there's a maximum flooding area on the upstream of this culvert. And we're also able to see the tailwater coming down here, so there's a tailwater condition on that culvert as well. So you can see the 2D does quite a good job of modeling that on the upstream end. Similar to that dynamic section, if I wanted to see what was happening there, I could come back to my view, visualization, and 12D has something called timelines. These timelines are just what we'd want to use if we wanted to see what happened in a 3D perspective view. So when I go edit a timeline, it's got descriptions of where my eye is going to sit, where my target is on the ground, and what results I want to take a look at. But if I go run that, it's got a timer up here. The major flow arrives at about 10 minutes. And so we're watching the minutes tick by there. In about 10 minutes, you start to see the flow arriving. And you'll see it starting to pond up at the upstream end. Okay. Now, you're getting slightly more discharge to the downstream, but you're able to see here that eventually it's going to fill up. It reaches its maximum, I think we saw in the graphs, at around 30 minutes or so. And then after the 30 minutes, it's the end of the storm, and we can see the water drain back down. So if we were to pause, I can stop that one. So that's the idea of using the 2D analysis, is that the 2D analysis is able to calculate the storage upstream and the flow through the culverts. So what I'm going to do is I'll zoom back into here, and let's take a look at the peak flow through here. It's let's make sure I've got the right results on. Yep, that's good done. 2D. So what we're looking at is that we're getting a flow down to about 2,000 liters per second going through that culvert. Same catchment flow at the upstream end. Okay. What's happening is that it's just got a different upstream area that it's using. We would expect those results to be very close to one another. So, just one moment while I just reach for my... A little bit of extra power required after you run a 2D analysis. All right. So, Hopefully what we did there is take a look at two different types of storage. We looked at just flat water storage with the 1D modeling, and we looked at the hydrographs with the TUFLOW. Now with the TUFLOW, you can't do flat water storage. It can't help but look at the hydraulic grade line that exists as the water slowly moves across the basin, but it is fairly flat. So now I want to take it to the next step. The next step I'd like to take a look at is if we're not just interested in the storage that's immediately upstream, okay, if we go back to the TUFLOW results, okay, before we saw that it was just a storage up here. What happens if we were interested in the channel storage that was upstream as well, plus the storage down here? Let's take a look at how we would do that with both the 1D and the 2D results. So let's clear up my screen just a little bit here. There we go. And once again, I'm going to turn off my culvert, and I'm going to add on another culvert that I've created, which has both the tailwater and some approach flows on it, channels. So what we're doing here, my plan is to take that 28 hectares and to move it up to the upstream reaches of these two areas up here. So the idea is now, as that water flows down the channel, we're going to take into account the channel storage. And we're going to do that first using the 1D analysis. So once again, we'll grab our network editor, and we'll take a look at how we do this in 1D analysis. So the first thing we'll do is we'll head across to the pipe tab. And on our pipe tab, there's a sub-tab for channels. And what we need to do is to pick a cross-section string, and 12D will then go and cut that shape from our data train model and load the data into the grid. So on this design tab, if I was to come here and add on my stormwater channel shapes, these lines here are just two-dimensional lines. They don't have any elevations on them, and if they did, we would ignore them. And the idea is that when you go pick one of these, that 12D will automatically drape that onto our design tin and get the cross sections for you. The elevations come from these, from the invert levels of the pits along the center line or the lowest part of the river. Let's take a look at that, what that looks like in a section view. So if I come to a long section, I might as well use the same one over here. Let's go profile that. And so what we're looking at now is the long section, and each one of these is another different shape. And eventually we get down to our culvert that goes underneath the roadway, and then we've got a bit of a tail race down here to ensure that we're accurately measuring the tailwater conditions on our culvert. So doing that all makes pretty good sense to us. Let's go and run that. I do want to make sure I use the same settings, so let's change that to a 3.4 as well. Come along and we'll do a storm analysis for that. And when we go run that, it's going to do the same thing as the previous run. It's going to run those multiple storm events to make sure that we calculate the critical flows and the critical elevations. So the difference between the first 1D and this 1D is the way that we calculate the storage. In this case, what we're doing, let me just go back here, and I'll go pick one of these downstream reaches. Head to that pipe down, channels. What we're doing is we're taking this channel shape, and we're assuming that that channel shape is consistent over this length, and we're putting it at the elevation of the invert, so we have that down here. So the volume that is going to be in this area is that cross-sectional area times 1/2 the length of that channel. So you can see it's a bit of an approximation down in this area. The other trouble when you get down into here is that you get a lot of cross sections that are close to each other, and there gets to be a concern about overlapping cross-sectional areas, which means you might be double counting or missing some of the storage. So now that I've showed you the two different methods, the final solution would be a hybrid solution, where first of all we would use the storage curve, the flat water storage in this complicated area down here, and the extents of that area would be defined by our maximum water level that we expected and that contour that we had before. And then upstream of that area, we would do the reach storage. So we'd be able to do a combination between the two. Now once again, when we go looking at results, if we go back to the results and we go ask for that, major storm, 25 minutes sounds like a good idea. And if we come back down and we ask to see that, come back down here, go ask to see the dynamic section, what we'd be seeing would be a section down all the channels, so that if we hit the play button on that, we'd be able to get a section view of the 1D flow, and you'd be able to see that flat water storage area where it was going flat, or almost flat, during the analysis. If we go back and play that one, let's pause that, go to max HGLs, and pause that there, that's what I'm looking for. You can see that there's very little energy losses across this reach here. So it is practically flat, but it's just a different way that we're using to measure the storage. All right, so let's close that back. Let's take back to our original screen and take a look at our progress. What we've talked about is we've talked about the hydrographs for the 1D modeling, and we've done both the channel and the flat water. We've talked about the hydrographs with the 2D modeling, but we looked at just the storage immediately upstream of the culvert. Now I want to come back and finish that last piece. So I'm going to come back once again. I'm going to turn off these models. And I'm going to add on my final culvert, which is my Stormwater 2D with an upstream. And let me, that'd be great. So what we've done here, once again, our drainage network editor will be required to take a look. If I come down to where we previously had put our catchment areas, catchment set number 3, I've gotten rid of the flows from there. And what I've done instead is I've created a node up above here. We call them bypass nodes. And I've put 60% of the catchment area up on this side. Use the same parameters. I'll go to my defaults for our catchments. Okay, same hydraulic parameters. And if I go pick on the other one, I put the other 40% over on this side. And so what happens now, I suppose also I could have put some portion down here to represent this part of the basin. But the idea is to split up the flow to the different reaches. Once again, I just might make sure that we use the same antecedent moisture conditions, so we're using the same values. Apply that and finish it. Okay. So what we're doing is we're ready to go run this one. Now when we run the storm analysis, we could simply go, I'm going to set up another default for this. Okay. So this was our previous road flow. The only difference that I've done this time is I've got a different drainage model that's here to pick up the upstream hydrographs. Now before I leave this one, we have been using the Ilsak's hydrograph or Ilsak's hydrology method. You don't have to do that. If you had your own hydrographs, you'd be more than welcome to come into any one of our nodes, come into this inflow hydrograph and paste your own time versus inflow here as well. So that's the option other than using the Ilsak's method. All right, so we will run the storm analysis on this one. Once again, when this runs, it's going to be running all of the events for the different storms. And you will notice it just takes a little bit longer to run this time. Essentially, when we're doing the upstream reaches, all the cells in this area are wet as well as this one. And cancel that, we don't need those ones. And what's happening is it's going all the way down here. Oh, by the way, I should explain what just happened there. It gave us a message saying that one of the result files were locked. So my apologies for that. Let me just come back and run that from the other area. File, data, layouts input. There we go. Yes, I do want to delete all my results before I start. All right, yes. So it is taking a little bit longer because these upper reaches here have wet cells as well. So just give that a minute to go and solve those. By the way, while these are running, If they pass the peak, I'd be more than welcome to hit the finish button on them, and 12D would read in all the results up until the point where the storm had finished. There we go. Now we'll come back in, and before we read those results, once again, we'll select the storm we're interested in looking at, and it's this 25-minute storm that I like. And we'll go read those results back in. And once again, if we go back to our 3D perspective view, turn off those previous ones, add in our new ones, which is our culvert upstream. And you can see that was the original view that we had when we started the webinar. Now, water levels and depths are, of course, are a crucial part. One of the other issues that does become very important is your velocity vectors as well, and understanding the velocity of your flows. So if I was to come back here and to turn off that first analysis, come back at the one that had the upstream and looking at the velocity results, what I'd be able to see are the velocity vectors showing the water coming down that channel. When it gets deep here, they will get a little bit smaller and then come out the tail race. If I was to take a look at these results and I wanted to play them over time, or if I wanted to change the length of those velocity vectors, I could double that scale and hit the set button on them to make them a little bit larger. And we're more than welcome to step forward and backward in time the same way we did for the water levels we saw in the 3D. Now, we've covered an awful lot of material over the last few minutes. Hopefully, we've addressed many of your thoughts or concerns and questions about modeling culverts and when upstream storage is important to the design. So that concludes the topic for today. I might just turn that over to Lisa for a moment to see if we've had any questions that have come in.
Thanks, Rob. We've had quite a few questions through. I think some of them might be a bit complex to answer simply on the spot, but I'll ask a few through and we'll see how we go. Firstly, John in Sydney has said several methods were presented today. Which one is the correct one?
I love that one. Yeah, we've talked about at least 6. In the world of hydrology, to ask someone what the correct answer is, you put a couple of hydrologists in the same room and you'll always get different answers. What the topic we looked at today was combining several different hydrology methods together with different hydraulic methods. So probably my bits of advice for this would be always ensure you use the proper hydrology method that would correspond to the hydraulics that you're planning on using, and make sure that those are married together well. So your hydrology and your hydraulics are generally go together as a pair. So make sure that that is adequately modeled. And if you're unsure, make sure that you find someone who has some experience in this field and get some extra feedback. The ultimate answer for all this, if there is an answer in hydraulics and hydrology, is calibration. If you've got some observed flows, observed water levels that compare your model, calibrate it against some existing conditions, and that's probably your best way to determine if you're on the right track when it comes to selecting the right method. So hopefully that one helps a little bit there, John.
Great. Fung in Queensland has asked how to plot entrance loss coefficient.
Okay. The entrance loss coefficients, if we can jump back, this is always a favorite question, especially when it comes to our dynamic. When we look at the dynamic, we currently, in version 11, we show all the pipe losses and the entrance losses together and only should plot it in one straight line. So currently, that is in version 11, we don't break up the pipe losses from the energy losses. So we don't plot them at the moment. So that's probably a good answer, or an accurate one anyway. What we do is when we present our reports, we will put the KU losses in our reports. Now, when we're talking about a culvert, there's 2 types of losses. There's, of course, the entrance loss and the exit loss. And those coefficients are constants, okay, when we're looking at culverts, okay, and this is specifically about culverts. If we're looking at stormwater pits, that might be a completely different issue. But let's go grab my network editor just for a moment. And I go pick that. Okay, the first thing that happens is when we selected this head wall type, what that did is that went and selected the entrance energy loss coefficient and the exit energy loss coefficients. And they're constants, so no, we don't plot them. But one of the options you can have with the pipe tab is you can come in and you can override those, both the inlet loss, the outlet loss, and you can put in additional minor loss. Each one of those uses the velocity at its corresponding position. So this is the entrance velocity times, so v squared over 2g times the loss, and an outlet and a minor loss using the velocity at the center. So with our culverts, we don't dynamically plot those for you, but you do have a place where you can put override values in. So I don't think that completely answers your question. I imagine that when version 12 comes out, one of the first things you're going to want to do is to take a look to see what we've done for that. So I hope that'll do for now. Thank you.
Sure. And Rashida in New South Wales has asked if there are any default rainfall files for 12D to run.
Default rainfall files, yes indeed. Probably more than you like to take a look at. If I go to our menu across here, and I go to our rainfall, if I click on this folder and head over to our library, we've received rainfall data from many places across Australia and the rest of the globe, and we try to include the ones that we can inside the folders, inside our library, pardon me. So yes, as you can see, there are different ones, okay? When you pull up any one of these examples and you read them in, if you did have your own IFD information, what I would suggest you wind up doing is going and clearing this out, keeping the rest of the data, but then putting in your own IFD data into those tables. So Rashid, I hope that helps answer your question. So yes, we do ship quite a few, but if we don't have the one for your local area, we've got definitely have a place that you can put your IFD information into it. And that IFD information is definitely intensity, so millimeters per hour. Okay?
Okay. There's a couple more here if we've just got a little time. So
Okay.
Adrian in Queensland has asked how the dynamic culvert tool compares to the rational method DNE that was shown at the start of the presentation.
Okay, that was the, which tool is that?
Dynamic culvert tool?
Oh, the dynamic culvert. I'm with you. All right, the dynamic culvert, if we come back in here, drainage 0, okay. Our dynamic culvert routine, what it does, it's going to use constant discharges. So if you compare that to the design method that you have inside the rational, they're very similar, exactly the same. They both reach a steady state for doing their sizing. This tool doesn't look at upstream storage, and neither does the rational, so they're the same on that. Where they start to vary is in the flexibility for additional losses and additional shapes. There's a little bit more that you can do inside the dynamic culvert. So for example, the losses, okay? With the rational method, you can specify your KU for your type for your inlet nomographs, but the entrance loss and the exit loss, or pardon me, just the entrance loss that's used during the hydraulic calcs under backwater conditions are hardwired in. With the dynamic culvert designer, you can change those. Another thing that you could do with the dynamic culvert is put in a sediment depth. And that has the effect of raising your invert, because the sediment's assumed to fill at the bottom, and of course reduce your cross-sectional area, therefore requiring greater upstream water levels to push the same flows through the culvert. So those would probably be the initial differences. Another difference is that when we go and solve these, the dynamic will do several different discharges at once, giving you a rating curve, where generally the rational one, you would run it several times and put your results into a spreadsheet to create it. So that's two types. I don't want to go on it too long because there's actually several different differences. When you start to look at road overtopping, and you go to set your weir data, there's several different weir types and road overtopping methods that can be used. When I first started this presentation today, I mentioned that I was not going to talk about the bypass just yet because it would be a topic for another day altogether. But essentially, you've got several different methods for doing weir type calculations, so we can split the water between going over the road and going through the culverts. So that's another significant difference between them. And then probably the last one that I can mention right off the top is the shapes. Okay, when you start looking at your pipe shapes, inside the rational one, we will do a rectangular and we'll do a circular shapes for doing the culverts. However, inside the dynamic one, we've got a lot of additional ones. You can have a custom shape, arch shape, of course, and the regular pipe and boxes. So there's a little bit extra that you can do inside the dynamic culvert design. One of the features that is quite popular is that you don't have to create a culvert inside 12D. If you want to, you're more than welcome, although I never did enjoy filling out numbers. You could type the numbers manually into all of these rather than picking an existing culvert. So if you wanted to just type it in to see what's happening, you could just do a calculation without actually creating a 12D drainage string, if you consider that to be a benefit. So hopefully that sort of answered that question for you. So yes, they are different. If you put in exactly the same values into both of them, you get the same answers. So that's probably one thing that you want to feel rest assured about. Or I should actually be more precise. I should say very similar answers. I should, just in case someone does want to know all the details, when the dynamic solves, it looks at the velocity, all the energy losses at the center of the culvert. And it uses the depth at the mid-chainage of the culvert. And then it looks at the inlet conditions and the outlet conditions. So there's 3 spots that it gets analyzed. When we do the rational method does a standard step backwater calculation through the culvert. So a little more detail in the hydraulic profile. We never show it to you, but we do a lot more detail in the hydraulic profile when it's operating under those backwater conditions. So when you're not running under full flow, so, there could be a slight difference in elevations, but they would be very small. So I sort of hope that answers your question on that one.
Thanks, Rob. I'll squeeze in one more before we finish. Ali in Canada has asked, is it possible to see whether we have inlet control or outlet control from results?
We've discussed that one in version 11, no. What happens is that it will change throughout the run, whether it's operating under inlet control or outlet control, depending on what's happening in your tailwater conditions. So what happens is we're looking at creating a graph for the in version 12, which will allow you to see as the job goes on which conditions, when it's running inlet control and when it's running outlet control, as it switches back and forth. And Ali, I know that's always been a concern for you, and when we get our 12 out to you, hopefully that's going to address that. And I'm sure there's many other people out there as well that would like to know just exactly when it's switching between those criteria as well. So look for that in the future.
Thanks for that, Rob, and thank you everyone for all your great questions. Sorry to those we couldn't get to live, but we'll answer you by email later. The recording of this webinar will be available in coming days through our website and our YouTube channel. We've got some more great webinars coming up, including one on dispute management, a conference case study, and a training webinar on chains. So do see our website for details of all of those. We'll keep updating it with many more topics in coming weeks, and also continue to keep you posted through email and social media. If you need to contact us in the meantime, we'll pop up our details on the screen shortly. That concludes our presentation for today. Thank you everyone for attending, and we hope to see you at future webinars.